right, we start out just with a few definitions. We have the metric, the distance, okay, the ds squared. In special relativity, you have minus dt squared plus the x squared plus y squared plus the z squared, or conversely, you have the opposite signature, which really doesn't make a difference. Instead of minus dt squared and plus for the spatial parts, you can have plus dt squared and minus for the spatial parts. It's the same thing as long as they're opposite sign. Okay, so one of them will always be the opposite of all the rest. The signature is always minus. R squared is the coefficient of d theta times d theta. By definition, we call that g theta theta. GA with one subscript is basically the square root of the GAA with two subscripts. G theta is the square root of the coefficient of d theta squared. Okay, the coefficient of d theta squared is r squared. So g theta with one theta is simply r. What is gt with one index? Okay, gt with one index is simply the square root of gtt. What's gr? It's the square root of grr. What is g theta with one index? It's the square root of g theta theta. What is g theta theta? It's the coefficient of d theta times d theta. In other words, r squared. Okay, do you see that? G with one theta is the square root of that, which is r. Okay, what is g phi? It's the square root of g phi phi, which is the coefficient of d phi squared. D phi times d phi. The coefficient is r squared sine squared. The square root of that is simply r sine theta. So we have these four quantities: square root of gtt, square root of grr, r, and r sine theta. Those are the four metric coefficients that we're going to be using, or square roots of the metric coefficients. In terms of the signature, obviously they're all 1 except for the one in front of the t, which is minus 1. Okay, a to a in the next line, that will be the signature. In other words, that will tell us whether it's plus 1 or minus 1. All right, so look at this page. Now, we're using an orthogonal system. We're using situations which are simple enough for us to use an orthogonal metric, so we're only going to have dxa, dxa, not dxa, dxb. Just the summation notation. We have repeated indices. So, okay. So you'll have some function g with two indices, GAA, times dxa, dxa. Okay. These little etas, a to a, a to b, those, if you remember, were the signatures. Those, like if you had a ds squared equals plus this, dx squared plus minus dy squared minus dt squared, whatever, the pluses or minuses were encapsulated in these little etas. So you'll have ds squared will be a sum of terms. Each term will have a square, dxa squared, and we'll have something in the front that tells us whether it's plus or minus. And then there's this GA. Now I deliberately put only one subscript on the G to tell you that we have to square it when you're putting it into the metric, okay? So look at the difference between the top line where it says GAA dxa dxa and the second line where it's GA squared dxa squared dxaa. You see that? Okay, all right. So basically we can write it as a square. If you had some function times dx squared, right? So you can write it as the square root of the function dx all squared. Again, if you have some function times dx squared in the metric, right? It's the same thing as the square root of the function times dx. Square the whole thing, and the function gets squared and the dx gets squared. Those eta, those are just plus or minus signs. Two metric coefficients, a and b. And multiply the two of them. You have GA times GB, and take the inverse, and multiply that by this whole thing in the squiggly brackets. Now, what are the two terms in the squiggly brackets? Look at the square brackets within the squiggly bracket. Look at those two terms to see the symmetry. Okay? The things in the bracket, the etas. It just gives you the sign. Can you see that you have A, B, B, B in one of them and B, A in the other one? Okay? Switch over in the first term from A, change every A to B in the whole thing. What do you get? Forget about the A, yeah, even the A to A, leave those in. Switch from A to B, like you did replace, global replace. A goes to B and B goes to A. What would happen?
It's the same.
It's exactly the same. And in the formula for the curvature, you're going to have products of these etas. So in which cases will the term A to B be 1, and when will it be minus 1? So the answer is, obviously, if both are plus or both are minus, then it's going to be plus 1. So if both of them are from the same, if both of them are spatial etas, then it'll be plus. You can't have two of them being a time eta, because you'll only have a time, something with something else. So it's just simply multiplying plus 1 times plus 1, or plus 1 times minus 1. The only time that you're going to get a minus is when one of them is what?
Nice.
When one of them is minus, right? And which means that what? That one of them is t and one of them is spatial. That's the only time you can get a minus out of that. Okay? Because that's the only time you have opposite signs.